Today, I will be presenting the core systems architecture behind Lunastadt, with a focus on how player-issued commands are processed, interpreted, and executed within the simulation. This presentation will follow a single interaction pipeline. We will begin with a basic command, spawning a tank at Hill Air Force Base, and then follow a second command, moving that unit to Denver. The goal is to demonstrate how the system transitions from raw natural language input to structured execution, and ultimately to autonomous unit behavior within a dynamic battlefield. The system begins with player input. At this stage, the command is unstructured text. It does not yet reference internal identifiers, coordinates, or system-specific actions. For example, spawn a tank at Hill Air Force Base. At this point, the system must determine both the intent and the parameters of the command. This is the entry condition for all player interaction. This input is received by the LM Studio ToolChat component. This system functions as the primary interface between player input and internal processing. Its responsibilities include receiving and normalizing input, determining processing strategy, routing the command into the appropriate interpretation pipeline. At this stage, the system decides whether the command can be resolved deterministically or whether it requires language model inference. For structured and commonly used commands, the system employs a deterministic parsing layer. This parser uses predefined patterns to extract the action, for example, spawn, the unit type, for example, tank, and the location, for example, Hill AFB. This approach has two advantages. First, it provides near-zero latency. Second, it ensures predictable and repeatable outcomes. Only if the command cannot be resolved through these patterns does the system escalate to a language model for interpretation. Once the command has been parsed, the system must resolve human-readable references into simulation objects. This is handled by the location resolver. Its role is to map inputs such as Hill Air Force Base into actual entities within the simulation, such as a military base sim instance with defined coordinates and properties. This system supports fuzzy matching, partial naming, and tolerance for minor input variation. This ensures usability without requiring strict syntax. Following successful parsing and resolution, the command is passed to the ToolExecutor. At this stage, the system transitions from interpretation to structured execution. The original command is converted into a formal instruction such as spawn_unit, open parenthesis, type, tank, location, Hill AFB, close parenthesis. The ToolExecutor is responsible for mapping intent to executable actions, selecting the correct subsystem, and passing validated parameters forward. The structured command is then handled by the UnitCommandSystem. This component is the central execution authority for all unit-level actions. It is responsible for spawning units, issuing movement commands, initiating attacks, and managing command-level validation. Importantly, this system enforces consistency by acting as a single point of control. No other system directly manipulates units outside of this layer. In the case of a spawn command, the system performs the following steps. Validate the target location. Tank battalion unit. Assign a unique identifier. Register the unit in the UnitRegistry. The UnitRegistry maintains the authoritative list of all active units within the simulation. At this point, the unit has been successfully created and is now part of the battlefield state. With the unit now instantiated, we transition from creation to behavioral execution. The player then issues a second command. Move Tank 501 to Denver. This command follows the same processing pipeline, parsing resolution execution. The system identifies the target unit via the UnitRegistry, the destination via the location resolver. This produces a structured command. Move unit, open parenthesis, 501, arrow, Denver, close parenthesis. The tank battalion receives this command. At this stage, control shifts from the centralized command system to the unit itself. The battalion operates as an autonomous agent. It is not continuously directed by external systems. Instead, it processes its behavior through an internal update loop. The battalion is updated through a centralized tick system. Rather than using individual update loops for each unit, the system uses a tick manager to update all units collectively. This approach reduces overhead, improves scalability, and ensures consistent simulation timing. Each tick, the unit evaluates its current state and determines its next action. As the battalion moves toward Denver, it uses a layered navigation system, road-based paths when available, land-based fallback paths when necessary, and direct movement when conditions allow. Additional safeguards include terrain validation, obstacle detection, and automatic replanning if movement fails. This ensures that units remain robust under dynamic conditions. During movement, the unit continuously evaluates its environment. Using a spatial partitioning system, it can efficiently query nearby units' potential threats and strategic targets. This allows real-time responsiveness without requiring expensive global searches. In summary, the system demonstrates a complete transformation pipeline. Natural language input, deterministic or AI-assisted interpretation, structured command generation, centralized execution, autonomous unit behavior. Each layer is designed to be modular, scalable, and fault-tolerant. The result is a system in which player intent can be expressed naturally, while still producing reliable, high-performance behavior within the simulation.